Hi everyone, I'm PradeepKumarReddyKambham. I would like to present my final project for the ADTA 5550 Deep Learning with Big Data course. So in this presentation, I'll be primarily explaining about the introduction of my project, architecture of my project, about the dataset and workflow that I have used in the project, the results, and finally the conclusion of my project. So let's jump into the introduction of my project. So what is deep learning? Deep learning is a subfield of machine learning concerned with algorithms inspired by the structure of function of the brain called artificial neural networks. Deep learning has become popular as the models are capable of achieving state of accuracy. A very massive volumes of data sets are used to train these models along with neural network architectures. Deep learning is using brain stimulations, hoping learning to make algorithms more efficient and simpler to use. I would like to discuss few points on what is the difference between deep learning and machine learning. So in deep learning, the performance of the model increases as the amount of input data increases. Whereas in machine learning, the performance graph of the machine learning model increases and does not improving with the increase in the amount of input data beyond a point. And in deep learning, advocates like solving a problem into end, whereas in machine learning, a problem is broken down into several parts and solve each problem of part and combine all the parts to get the final result. Testing a deep learning takes much less time, whereas testing a machine learning model takes much longer time as compared to deep learning model. I would like to discuss more about the supervised learning and unsupervised learning. These two supervised and unsupervised learning models are two different categories. Under supervised learning, convolutional neural network CNN and recurrent neural network RNN and artificial neural network ANN are considered. Under supervised learning models, autoencoders, Boltzmann machines, self-organization machines are considered, and these are two different. But most of it has distinct features. But the most integral point of this of difference is how these models are trained. While supervised models are trained through examples of a particular set of data by the unsupervised models are only given input data and does not have a set output outcome. They can learn from so that the field that we always trying to predict is not there in any unsupervised model. While supervised models have tasks such as regression and classification and will produce a formula, but in supervised models consist of clustering and association rule learning. So these are some of the important models I would like to discuss about. Coming to the architecture of artificial neural network ANN and the recurrent neural network RNN and convolutional neural network CNN. Coming to an artificial neural network, what is an artificial neural network? It is also called as feed-forward neural network because its inputs are processed only in the forward direction. And this is actually group of multiple receptrons or neurons on each layer. Some of the advantages in this is it is capable of learning any nonlinear function, and hence these networks are popularly known as universal function approximators. One of the main reasons behind the universal approximation is the activation function. It also want to discuss about the couple of challenges with artificial neural networks while solving an image classification problem. using artificial neural network. The first step is to convert a 2D image into a one directional vector prior to the training itself. And this has like two drawbacks. The number of training parameter increases drastically with an increase size of any image, and also artificial neural network loses the spatial feature of the image. Coming to RNN, RNN has a recurrent connection on the hidden state is looping constant, ensures that sequential information is captured in the input data. We can use RNN to solve problems like time series data, text data, audio data. Some of the advantages of these are like RNN captures the sequential information present in the input data that is dependent between words intake while making the prediction, and also if you see the output of each time steps depends not only on the correct word but also on the previous word as well. And in RNN, this hits the parameters across different time steps. This is popularly known as parameter sharing. Also, this RNN application has few challenges. One of the common challenges is it suffers from vanishing and exploding gradient problem. This problem is usually a common problem for all types of neural networks. So coming to the convolutional neural network, CNN, I would like to discuss more in detail about the structure of CNN. As most of my project involves more of convolutional neural network, I'll give more detail about CNN. Let's see what is CNN. The CNN refers to a subcategory of neural networks. Therefore, they will have all the categories of neural networks. However, convolutional neural network is designed to process input images. Their architecture is more specific and it is composed of two main blocks. If we break down the first block makes the particularity of this type of neural network. Since it functions as a feature extractor, to do this feature extraction in a template by matching, applying the filtering operation. The first layer filters image with several convolutional kernels and returns feature maps, which are then normalized, resized usually. So this process can be repeated several times. We filter the future maps obtained with new kernels, which uses a feature map to normalize and resize. We can also filter again and again and so on. Finally, the values of the last feature map of a concatenated feature map are concatenated into a vector. This vector defines the output of the first block and input to the second block. Coming to the second block is a characteristic of first CNN. It is in fact at the end of all neural networks used for classification. The input vector values are transformed with several linear combinations and activation functions to return a new vector to the output. Thus, this last vector contains as many elements as there are classes elements or different elements in this. Each element is therefore between 0 and 1, and the sum of all the words is equal to 1. The probabilities are calculated by the last layer of the block and therefore of neural network, which uses a logistic function or a softmax function as an activation function. As gradient backpropagation, the cross entropy is minimized during the training phase. But in case of convolutional neural network, this parameter refers in particular. Let's discuss about the different layers of convolutional network. There are mainly four different types of layers for a convolutional neural network. The first would be the convolutional layer, the next is pooling layer, and the next is the activation correction layer, and then fully connected layer. Coming to the first, this is the convolutional layer. The convolution layer is the key component of neural networks and is always at least the first layer. As I said, it its purpose is to detect the presence of a set of features in the images issued as input. This is done by convolutional filtering. This principle is to drag the window representing the feature on the image and to calculate the convolution product between the feature and each portion of scanned image. So a feature is then seen as a filter. The two terms are equivalent in this context. The convolutional layer does not receive several images as input and calculate a convolution of each of them, which each filter, this filter corresponded exactly to the filter we want to find in a particular image. Now that we get for each pair, which is image, and filter a feature map, which tells us where the features are in the image. The higher the value, the more corresponding place in the image replaces or resembles the feature. When it comes to next layer, which is pooling layer, this type of layer is often placed between two layers of convolution. It receives several feature maps and applies the pooling operation to each of them. The pooling operation consists of reducing the size of the image while rescuing the important characteristics. To do this process, we cut the image into regular cells and we keep the maximum value within the cell. Usually, smaller square cells are often used to avoid losing too much information. The pooling layer generally reduces the number of parameters and calculations in the neural network. This improves the efficiency of the network and avoids learning. Coming to the next layer, the correction layer, which is an activation filter. The correction layer replaces all the negative values received as input by zero. It acts as an activation function. The last layer would be the fully connected layer. The fully connected layer is always the last layer of the neural network. Convolution or not, this type of layer receives an input vector and produces a new output vector. To do this, it applies a linear combination and then possibly an activation function to the input value received. Lastly, the last fully connected layer classifies the image as an input to the network and it returns a vector of size n, where n would be the number of classes in a specific image classification problem. Each element of vector indicates the probability of the input image to belong to a class. The convolutional neural networks learns that the weight values in the same way as it learns the convolution layer filters during the training phase by back propagation of gradients. Coming to the first part of the project, we need to find a data set that consisted of images or audio files that was also able to perform deep learning. So I found a chest X-ray dataset. It is an image-based dataset, and this dataset is collected from Kaggle.com. And this dataset consists of 5,863 X-ray images of two categories. One is pneumonia and another is normal. This dataset is organized into three folders. They are train, test, and validation. You can see the images of the datasets on the right side of my presentation. Coming to the part two of datasets. So we are going to do what the majority of my content is like building, training, and testing, developing a convolutional neural network for the Cipher 10 dataset. So there are around 60,000 images like animals, vehicle classes, and there are also labels. So each image is colored image. So there is three color channels, and size of image is 32 by 32 by 3, and there are like 10 classes with 6,000 images per class, and they are coded within the range of 0 to 9, and 10 classes in the dataset. They are like aeroplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. The dataset is classified into two categories. There are 50,000 image. There are 50,000 images in the training dataset and 10,000 images in the testing dataset. In this picture, we can see some of the sample images in each class in Cipher 10 dataset. So before we are able to build our neural network, we have to first download the dataset from Canvas, and we need to spin up a virtual machine, and we need to upload the dataset into the virtual machine. We can see in this slide, like we have created a virtual machine in the GCP platform, and we have uploaded the Cipher 10 dataset into a folder called as Jupyter Notebook, as shown in the picture. So next, after uploading the dataset into the virtual machine, I'll open the Jupyter Lab in the virtual using the virtual machine, and you can see and upload. I mean, I can just import all the data sets into the Jupyter Notebook, as shown in the picture here. So till now we have seen how to download and how to upload the data set into the deep learning VM. So for the next part of the project, we need to build, train, and test the convolutional neural network using the Cipher 10 dataset. So this is the diagram I have created to show the convolutional neural network with a Cipher 10 dataset with the two convolution layers. So the first part of the diagram is the input, and the size is 32 by 32 by 3. It is 32 by 32 because the actual size of the image that is being input to the model, and 3 because the image is on color scale. That means that there are 3 color channels. So the first convolution layer was 28 by 28 by 6, and the first pooling here was 14 by 14 by 6, and the second convolution layer with the 10 by 10 by 16, and the second pooling layer is 5 by 5 by 16. So after all the convolution and pooling layers were created, the last layer was flattened, and to go into the model for it to be trained and tested, there are 3 fully connected layers in this model. By importing the data to Jupyter Lab and defining all the supporting functions to build, train, and test the CNN model, which I have created, discussed. I set up all the quick convolution layers to model, and I want to check the accuracy of the model. So I ran the Python program and the results are as follows. There are like 49 steps with each step of 100. For initial step, there is about like 10.3% accuracy and gradually increased in step 10 to 16.6%. And from the 10th to the last step, it is increased from 60% to say like 68.34%. And we can see the accuracy here. Accuracy is around 62.43% for the Cypher 10 dataset. So the next step of the project is comparing the convolution neural network for Cypher 10 dataset and the convolution neural network model we created for the MNIST dataset in our previous assignments. So these two datasets have a lot of common things. Both are like image datasets, and they are strive to achieve the same output. They are like both image datasets, and they want to produce a label as their output. And as I already discussed, the Cypher 10 dataset has around 60,000 images with 50,000 in training and 10,000 in testing. And images in and around are like most probably the vehicles and animals. Values labeled from like 0 to 9, and there are like 10 classes in Cypher dataset, and images are of size 32 by 32 by 3, whereas in MNIST dataset there are around 70,000 images, in which 60,000 are from a training dataset and 10,000 images from a testing dataset. These images are handwritten digit images, which label like 0 to 9, and there are also grayscale images with black and white, and these images are of size 28 by 28 by 1, so they are a little bit smaller than the Cypher 10 dataset. These are some of the examples by Cypher 10 dataset, like a truck and vehicle as shown in the picture there. And these are examples of examples for the MNIST dataset, like which contains handwritten digits like 504192131. Okay. So in this slide, I want to discuss about the CNN model for the two data sets. Cypher 10 dataset and MNIST dataset. The convolution neural network structure for both models are similar, but the only difference is the size of the input image for Cypher 10 dataset is like 32 by 32 by 3, which is bigger than the input MNIST, bigger than the MNIST dataset input images. It is like 28 by 28 by 1, which is smaller image. First convolution layer was 24 by 24 by N1, and the first pooling layer was 12 by 12 by N1, and the second convolution layer was 8 by 8 by N2, and the last pooling layer was 4 by 4 by N2, and the last one went by like 5 by 5 by 16, and then both are connected to the flattened, both are connected and flattened into one-dimensional vector to get fit into the fully connected layers. But the size difference is overall in the model. So in this slide, I'm going to discuss about the output accuracy for both the data sets. And these are the steps 0 to 49 for both Cipher 10 and MNIST datasets. The difference from step 0 to step 10 in the Cipher 10 is from 10% to 60%, whereas for MNIST it is around 9% to 98%. There is a drastic difference for inaccuracy in the first 10 steps in the MNIST dataset, but from 10 to 49, it is increased from 60% to 68%, whereas in the Cipher 10 dataset, but 98 to 99% in the MNIST dataset. We can see there is a little difference in the MNIST dataset compared to Cipher 10 dataset. This is due to the size of the input image to the Cipher 10 is the Cipher 10 is comparably like bigger than the input to the MNIST dataset. If we plot Cipher 10 and MNIST dataset accuracy, we can see like there is a drastical change from step 0 to step 10, and from 0 around like around 90s, and whereas in Cipher 10 we can see like a 0 to 40 and then 40 to 50, and it has gradually increased up to 68%. So this is the result. And comparing the Cipher 10 and MNIST dataset accuracy, I think the following possibilities are considered, because as we are using the convolutional neural network architectures for both the datasets, after accuracy will be changed, because MNIST dataset is a grayscale, while Cipher 10 dataset is a color images. We have used filter size of 5 by 5 for both the models. This is a chain of cap and the test results. In future, we can try with other filter sizes to vary our results. For MNIST model was trained for 5,000 steps for batch size of 50 and was considered, and after every 100 steps, we make the model to evaluate and test the data. But the Cipher 10 model was trained for 5,000 steps, but the image batch size of 100 was considered. And after every 100 steps, we could make a model to evaluate on the test data. I also feel like dropping off a layer probability value because the probability value matters a lot for accuracy differences for both data sets. So coming to the final part of my project is to redesign the architecture of Cipher 10 dataset. So I added one more convolution layer and a pooling layer to the existing convolution neural network models. So there are total of 3 convolutional layers and 3 max pooling layers and 1 flattening layer and 1 fully connected layer and 1 output layer. I want to check how the accuracy will increase by adding 1 convolution layer to the existing CNN for Cipher 10 dataset. And I ran the Python program, and the following are the results. By redesigning the CNN model for Cipher 10 dataset, I got accuracy of around 72%, which is better than the original model. So it is understood from this, if we add more layers, then the model will learn more, and there is a chance of achieving good accuracy and validation, which will not make a model leads to overfitting, and we can attain good test accuracy as well. So this is like after adding an extra layer, these are the results. And so when it comes to conclusion, this project like compares the model performance between the original CNN model with the redesigned CNN model on Cypher 10 days. That approach of using redesigned CNN model is better than the original model to boost up the performance of the model. This result can be still improved with the help of pre-trained model or performing hyperparameter tuning. In future, with increasing depth of CNN model and with the help of pre-trained model, we can increase the performance of the model. Other features, extraction methods can also be used, such as using transfer learning to extract features and can get good test accuracy. And thank you.